Right, thank you so much. Thank you so much, Yang, for the nice introduction. I also wish to begin by acknowledging the traditional owner of the land on which we're gathering today and pay our respect to the elders past, present, and emerging. I want to say I have long association with MGSE and the University of Melbourne, where I obtained both my master's and PhD degree in science education under the supervision of Professor David Clark, who unfortunately left us in January last year. So during my 8 years at MGSE, I also worked as a research assistant for the Learner's Perspective study. I think some of you know the study, which is an international comparative study of mathematics classrooms. And then as Yang pointed out, I was a postdoctoral research fellow as part of the ARC project, also led by David at the International Center for Classroom Research. So I was delighted to be invited by Yang and Wei Chun to present this webinar as part of the Math Science Technology Education Group Research Webinar Series this year. So I suppose in this talk, what I'm going to talk about is I'll first outline the imperatives of STEM integration, which is a broader context that has been dominant in the public and research discourse, not only in Australia, but internationally, and then present a case for interdisciplinary mathematics and science in the context of primary schools. In order to support this interdisciplinary argument, we'll then share findings from ARC project, the AIMS project, led by Professor Russell Tytler, who's in the audience here, as a context for discussing some of the opportunities and challenges associated with both the teachers' enactment of the pedagogy, but also the assessment around student interdisciplinary learning through this guided inquiry approach through representation and construction. We'll then draw some implications and discuss future research in this direction. So first of all, I want to talk about the imperatives that has been dominant, I suppose, in the public discourse and research discourse as well. So there are three imperatives I want to talk about. The first one is the social imperative, and then the second one is the economic imperative, and the last one, which I'll talk about, is the relevance imperative. So I suppose the social imperative, researchers often talk about that we are living in a world full of interlocked complex systems, where a complex system is a system composed of many components which may interact with each other. So examples of such complex systems are global climate, the human brain, transportation systems, economic systems represented by the stock market graphs, or the technology system, just a few examples there. So many of those most powerful things that impact our life are systems. Therefore, I guess the argument there is appreciation and understanding of the world as interlocked complex system are critical, both for us as individuals, but also a member of the community. So that's a social imperative you can see from some of the public discourse around the STEM integration. The second imperative, of course, is coming from the economic perspective, which has been, I guess, predominant to the public discourse around STEM. In Australia, for instance, education in STEM has been promoted as a solution for preparing future workforce for economic prosperity. And similarly, the introduction of STEM education in the United States, for example, was also intended to address the STEM pipeline problem, which is around the declining of the number of students pursuing the STEM field. So there are quite a number of reports that generate in the past few years, so I'll only mention two quite briefly. So the first one is coming from the Office of Chief Scientist. That's an occasion paper where they surveyed employees regarding the type of skills that are most important. So the top 5 skills, as you can see on this diagram, including learning on the job and critical thinking, problem solving, and also interpersonal skills. This is also consistent with the more recent report generated by the Foundation of Young Australians, where they looked at the type of skills required for future workers. One of the things I want to point out on this diagram is where you'll see that 77% as identified that workers will spend more time using science and mathematics skills. So that's pointing to the importance of science and mathematics, which is the topic of this talk here. But what I want to propose is really to looking at the argument about STEM integration from the relevance lens. So Newton identified relevance as a relationship in the presence of some needs, aspiration, expectations. He also differentiated the internal relevance from external relevance. So for him, internal relevance refers to the connections between knowledge within a discipline or across a discipline to produce a highly structured, coherent, and unified body of literature of knowledge. Whereas external relevance, in contrast, is more outward looking. That is linking to the body of knowledge to people's needs and expectations and aspirations, which I suppose has been widely documented in terms of the benefits of teaching STEM in a more connected matter, relate to the relevance to students and teachers and their engagement, learning disciplines, and also the 21st century skills, which is quite similar to the STEM skills that mentioned in the previous slides. I guess here is just an example where the girls that the project we are working with some of the Geelong schools where the girls are engaging an authentic problem-based approach where they translate industry posed problems into something that they have ownership of, which demonstrates the huge impact in terms of this approach, helping the girls to see themselves as for them to see that the relevance of what they learn in schools by connecting to the communities and local industries. So there's lots of benefits, I suppose, have outlined in the literature around STEM integration, but there's lots of challenges as also identified. So in this talk, I will talk about those 3 challenges around curriculum design, pedagogy, and also assessment, which I hope to address or at least touch upon in this presentation. And this diagram by Joanne Vasquez and others has been widely cited, where they conceptualize STEM integration along at various levels. So in this presentation, I'll talk about the interdisciplinary level that they outlined, but with a slight different takes on this level. So this takes me to make a case for interdisciplinary maths and science and in the context of primary schools. So why and how we do interdisciplinary work in science and mathematics. As what Young and David outlined in their STEM Education Conference presentation in 2016, is what they argue is interdisciplinary work requires interconnections amongst those disciplinary boundaries rather than demolition or compromising those boundaries. The reason for that is each discipline has the internal coherence of knowledge systems and practices that support the generation of those knowledge. So, however, I guess one of the arguments from the interdisciplinary perspective, especially in science and maths, is that there are a set of common epistemic practices underpin both disciplines. Those include data modeling, identify patterns of relationship, but also qualitative, quantitative reasoning, as identified by a number of people there. And Richard Lehrer, in a more recent work, pointing out that children can also be encouraged to see the similarity and contrast in the ways of knowing and reasoning that has been favored in the different disciplines. and engaging this fruit form of epistemic dialogue to appreciate why we do certain things in certain ways rather than just taking as for granted or being given those information without further explanation. So this takes me to the project, the ARC project, Interdisciplinary Maths and Science Learning project. You can see the website, project website there, if you want to find out more about the project. So as I mentioned, this ARC project is led by Professor Russell Tytler and in collaboration with quite a number of people across multiple institutions. So we are in the final year of this project. The key features, I suppose, for this project is to one of the key aims is to help students to deepen their learning through linking science and mathematics. We also work closely with the teachers in terms of collaboratively planning and also delivering or enacting the sequences with the teachers. There are some common features of those sequences that we designed, which I'll share in a moment. The focus is on representational construction by the students, and also there's a focus on mathematical modeling. We also adopt or employ this guided inquiry approach where the students have opportunities to invent, reviewing and refining representations. So as part of the project, we also follow a group of children longitudinally over the 3 years in order to see whether there's any cumulative gains, which we are still working towards for our data analysis. So this slide outlines the IMS pedagogical model, which was developed and refined in the first 2 years of the project. So as you can see, it comprises of 4 stages. So I'll unpack each of those for you. So the orienting is the first stage where often the teacher either challenging or support student to notice certain key or productive features of the situation or phenomena that they're looking at, and establish the need for them to explore that further through constructing representations. In the second stage, which is posing representational challenges, where a student invent and generate representations that to helping them to generate claims about the phenomena or making predictions. In the third stage of this pedagogical model, the teacher guided the sharing and reviewing of the clarity and adequacy of the representations, often drawing on the variations in the student representations to move them towards a consensus. And the last stage of the model involved the student responding to the new or related representational challenges, so to consolidate the learning that they have gained through the other phases. So as I mentioned, this pedagogical model, of course, is developed and refined in the first 2 years. So we didn't have this pedagogical model to start with for the project. Whereas this was coming through our analysis of teachers' practices. So in the first part of the talk, I will share some of the examples from one teacher who enacted this pedagogy and to identify what other opportunities and challenges are arising. The other aspect I want to emphasize here is you might recognize the similarity between this model and the 5 E's model or the inquiry model that you might come across. What I want to point out is that the evaluation part of the 5E model is embedded across all the 4 stages here. And also for the IMS model, we have emphasis on representational construction by the student, which you can see there. Also, I want to emphasize is often when you look at how this pedagogy is unfolding in the classroom, it's taking a more iterative manner rather than as linear as often demonstrated in diagrams such as this one. So what we, I suppose, for the project, what we employed is the design research methodology, where we're working closely with teachers through workshops, planning meetings, and discussions. The data were collected through video capturing and various methods to capture the student work and also interviews. As mentioned, the pedagogical model, we have been refining it as we're going through the process in the first 2 years. So what I'm going to draw on today is to utilize those resources, those data sources that has been obtained from one of the classrooms that we have been working with. So I want to, I guess, speak to those two questions. So the first question related to the challenges and opportunities when a teacher, one of the teachers that I'll be talking about, how he enacted the IMS pedagogy in the classroom, and what are the challenges and opportunities emerge as part of the process. The second question related to the so what question. So what is the interdisciplinary learning and how we can assess that learning based on this type of approach. So the research context, just give you a brief overview of a research setting and context. So the research is conducted in a private K-12 college in regional Victoria in Australia, and the teachers is an experienced teacher with a master's degree in education. So at the time of the data collection, he's been working as a science specialist for the grade 5 students for a class, but he also worked as a grade 6 classroom teacher. So this is the grade 5 classroom that we are focusing here. And the students, including 22 students, and we also follow 6 students selected by the teacher, which represent a wide range of academic abilities there. So how the teacher enacted in the IMS pedagogy. I will talk about this, the enactment through this, the chemistry sequence, where the intersecting concepts for the science and maths is around states of matter, particle model, and in particular evaporation, which is our way of be focusing on, and the idea of volume, area, ratio between area and volume in particular. So the first, I guess, stage of the IMS model, as I outlined, is orienting. In this example, the teacher helping the student really had a discussion with the student in terms of how they think about water existing in different forms or states. This is an example where the students, Jenny here, who's draw some particle models, draw some dots on the whiteboard to demonstrate, I guess, her idea in terms of the arrangement of the particles in each of the different states. And the teacher draws student attention to the spacing between the different states of matter, as you can see in the episode here. So given that the drawing is quite static, without necessarily talking about the motion of the particles, the teacher then introduced 2 more demonstrations using the phenomenon of diffusion to helping students to orient towards the motion of the particles, but also then linking them, helping them to think about the motion of our particles in different temperature conditions, which is in the example of the food dye in a hot and cold water, as you can see there. The teacher then presented or posed a representational challenge for students to represent melting and evaporation by heating up ice cubes on a hot plate, and get students to share what they see, what they imagine would happen to the molecules when they were heated. So this is a representational challenge that has been presented. So in this case, I guess what the task asks the student to do is to turn the material, the perceptual experience of seeing ice being heated, turning water and eventually evaporated into gas, into visual and written signs. What we identify from the student responses is a variety of responses. I guess there's huge variations. What you see is 3 examples here. Each demonstrate the student pay attention to the different aspect of the phenomena and using different ways, invent their own ways to show those ideas. So the first example where the students was showing the spacing, but also the movement of the particles in the gas state. The second example is quite interesting, where the student were talking about how the particles escaped into the liquid when ice was heated, which is quite different from the first example. The third example there, again, was an interesting way where the student tried to represent the movement of the particles by using the little dashes on the side, as you can see there, but also try to link to the idea of temperature, as you can see. So the point here, I suppose, is the power of, I guess, getting students to represent the ideas is really the visual representations helping them to communicate those ideas more clearly, which often tend to be glossed over if we're just looking at the written form of their explanations. So the second set of representational challenges that has been proposed in this classroom is where the teacher asks the student to investigate and explore the rate of evaporation by using different sized and shaped containers. So the student will ask to generate hypotheses in terms of which container going to lose the most water over the period of a week, and also then they come back after 1 week to record data and draw conclusions. So those, again, are some examples where we looked at student examples to see how they utilized visual representation to show some ideas. And you can see the variations again there. Some of them seem to depicting the processes, and other representations where the students started to draw some causal relationships based on their representations there. So the mathematic, in this task, the student were asked to mathematizing the evaporation problem, which is looking at the rate of evaporation as changes in the volume and surface area. So this is an example where the student tried to work out the surface area of different containers. And because this is the containers, as you can see, they are of different shapes. And the mathematical level is quite beyond what the students are at grade 5. So what the teacher did then is to help them using formulas available on our website to work out the processes, working out the areas which you can see on the right side, the diagram there. So in contextualizing the concept of rate using both the surface area and the volume there, what the student need to do is to coordinate the 2 data sets there to be able to draw some conclusions. So what you see here is 2 different examples where the student try to coordinate and to understand and draw conclusions based on the data they recorded. And the teachers, after giving students a chance to report their result and try to bring them back together in terms to think about the relationship between the surface area and the volume of water that has been lost, and try to establish the connections and to helping them to develop the scientific explanations. So, so that's just a case where the teacher provide illustrative case of where the teacher enacted the IMS pedagogy. What you see is where the teacher set up a series of perceptual experiences for students to orient student attention to certain aspect of the event, and also provide the opportunity for students to imagine, invent, and represent, which is showing in the variations in the student representations there. But one of the challenges, as also I hinted across in the presentation, is often what we're trying to do in the sequence is for the student to turn in their perceptual experiences, such as observing the evaporation phenomena, into different science systems and through linguistic, visual mathematics. And in this case, in particular, student has been used to a linguistic account of explanation. So moving beyond just using linguistic account has been quite a challenge for both the teachers and for both the student and the teachers. The other challenges arising from analyzing the data such as this is, even though the teacher made an attempt to coordinating and bring student ideas together, there was quite limited discussion around the variations in the student-generated representations, partly due to the time limit. Often the teacher ran out of time to have a proper discussion. It could also be due to this is the first time the teacher taking on this approach, and it does a quite demanding approach for the teachers to be able to know how to guide students, discuss those variations in the representation towards agreement. So I guess the question, of course, there's a lot of opportunities, as you can see, emerge, and also the challenges. The next question is, of course, the so what questions. So what students learn from such an approach? I won't talk about this analysis in detail because it already published, but I'll just give you some snapshots of the type of learning that we identified by looking at the student work. So this is a study that we did from the same classroom, but in a different sequence, which is the physics topic. So the intersecting concepts between science and math is around light reflection. And the math idea is angle and symmetry, which is the focus for this analysis. What we're trying to do here is to identify ways to categorize, but also assessing the levels based on the student representation, which is quite a challenging task, as you could probably expect it. So in this analysis, we developed assessment rubrics for each task to identify, to look into those student work to see what is represented and what the meaning that we can infer from that, which of course is not straightforward, which I'll talk about those challenges a bit later. So we, using those rubrics, we differentiate the 3 different levels. So the beginning level, where the students depict what they see without necessarily using those ideas from the science and maths to generate explanations. The second one, the developing one, where you can see the examples where the students starting to identify how the light travel in the periscope. This is the periscope task that the student worked on, but without any necessarily the directionalities or the angles that on those designs. The last one is a consolidation, where we can see where the students starting to use both the science ideas, the conventions, using arrows and to indicating how the light travels through the periscope, but also then labeling the angles and have some indications of symmetry in their design of the periscope. So that's the assessment rubric we developed for each of the tasks, which allow us to then identify and to see whether there's any cumulative learning gains. So the second part of the analysis is, of course, we look at the pre and post test, as you can see on the top two diagrams, and also together with the work samples to get a sense of whether there's any learning gains by just looking at the example, but just looking at the student work samples, but also through their interview account. So this is a student which is, you can see there's very limited or little change from pre and post lessons. And also in the interview, there's very basic understanding that has been demonstrated in terms of understanding the idea of reflection. Whereas these students seem to develop some understanding as a result of sequence, but she's still quite confused in terms of directionality. So she's still grappling with how to use the conventions, which is straight lines and arrows, to represent how light travels, and involves the use of the idea of angles and symmetry. Josh is an example where more advanced, where he was able to draw those using straight lines and arrow to identify the directionalities of the light path, but also to bring in the mathematical idea has been introduced in the sequence, as you see. And he also mentioned both the sciences and maths in the interview as well. Stan is another, the last example from Stan is quite interesting because, as you can see, there's quite different ideas as being presented in the pre-test and the post-test. So the post-test is demonstrate to us there's changes in terms of the meaningful use of conventions to show the directionality of the light path. And he's also very articulate in his interview. You can see the use of those scientific language and to describing the principles, what he called the principles of light reflection. He also discussed and talk about the power of visual representations. In fact, he has been quite used to use linguistic account, whereas visual represented ideas visually was quite challenging. But by the end of that sequence, he's really talking about the power of represent ideas visually, as you can see in the interview there. So what does the teacher say from based on this type of approach, and what does this teacher identify as a learning? So from this teacher's perspective, he sees that the student actually learned a lot, and he used the example of using the complex language that he heard them saying in the classrooms. He also commented on the maths in terms of the power of maths, where he thinks that given that he was a science specialist, he was commenting and reflecting on the opportunities or missed opportunities that he could really working on the maths for the students there. So there was some dilemmas that this particular teacher faced. And he was also, I guess, in both interviews after this chemistry sequence and this light sequence, he was talking about the idea of mathematics, where he really starting to see the value of maths and the authenticity, which is a word that he has been talking about. And he see the purposeful use of the maths, how the maths can help really, can help the student to develop scientific understanding and vice versa. As hinted before, the students and the teacher, this is a very new approach for both the teacher and for the student to visualize the ideas. So in this interview where the teacher commented that the idea of representation is quite new, but he started to see the importance of representing ideas, for students to representing ideas, not only verbally, but also visually, as you can see from these slides. So there are some indications of both student learning and teacher learning, as you can, we can identify from our data. So, so what can we learn from, I guess, the analysis? What we encountered, I suppose, try to identify the interdisciplinary learning in terms of student work. Is often we involved in, as a research team, we involved in the discussions around what we're trying to do. What are the expectations of the students? What is the curriculum expectation? So it's not as straightforward as just looking at your piecework and then be able to identify the levels. There's also challenges in terms of developing the rubric, which I hinted before, is what we find out is, as we're going through that process, is we really need to develop those task-specific rubrics that can capture the nuance of each of the tasks. And one of the challenges is, of course, the student representational competence do not always align with this topic understanding, as we see in some of those examples. So in that case, what can we do in terms of assessing student learning? What we identify in the analysis is some modest learning gains, which is initial exposure to the new approach. So for the project, for the ARC project as a whole, we are still working on whether those learning gains can be building to a short-term or long-term, even long-term learning gains as the student exposed to this approach over the 3-year period. So that's something we are still working on. So that brings me to the final part of my talk, which is about implications by drawing those ideas together. So what can we draw from both analysis, looking at the challenges and opportunities associated with teachers' enactment of the pedagogy, and also assessing student learning in both science and maths? What we find is that even though the project is attempted to balancing and maintain the disciplinarity integrity through the use of representational challenges, which provide natural intersections of those concepts, we also find that student understanding and representations of the mathematics, which is not surprising, I suppose, in those cases are not as strong as the science there, which is something has implications for future study or similar studies looking at interdisciplinary approach. The second point, I guess, is more in terms of the progression from inventions to conventions. So what we see from those student examples is there's lots of creative inventions, but the question arising is, of course, when and how and when those relevant conventionalized form should be introduced, whether it's in maths or the science. And further, how to support the integration of science systems across the different modes, as we talk about the linguistics, the visual and mathematics, and also across the two subject areas. So lastly, I suppose there are also implications in terms of teacher professional learning. Even though the teachers that we presented here has strong discipline knowledge, to take up this interdisciplinary approach, it does mean that the teachers need a deeper disciplinary knowledge to be able to guide and when and how, or when and why they should shift focus between the two subjects and from the science to the maths and maths to the science. And the pedagogical content knowledge is another area that is required to really guide students through inventions to establish consensus and moving students towards an understanding of the conventionalized form of science or mathematics. And the last one is those generic expertise required, those flexibility, creative problem solving, and adaptability is required when the teacher encounters those novel teaching and learning situations. So that leads to the directions in terms of future research. So one of the studies that as Jan already mentioned earlier, one of the study we just starting this year is really to tap into teachers' knowledge and what we call adaptive expertise, and to identify how the teachers, the nature of that adaptive expertise, but also to track the development of teachers' adaptive expertise in the context of interdisciplinary mathematics and science. So that's a project we are currently work on, and we're hoping that we can take some of the findings in a couple of years' time and to report back to the group here. So on that note, that's the end of my talk, and I would like to thank you everyone for your attention, and I would welcome any feedback and comments from anyone.